Okay, so we're looking at Chapter 10, and Chapter 10 is going to be about linearizing data. And what that means is that we talked a while at different times about having a data set that was really just, it wasn't normal, it wasn't anywhere near normal, so we were going to have to transform that data set. And that's what we're talking about here, is transforming information. What I have here is I have a spreadsheet of data, and I've got values here in the A column in Excel spreadsheet here. And these are my independent values, and here in B are my dependent values. And what I'm going to do is I'm going to pull up what this looks like as a scatter plot. Okay, and I've crossed everything else out here so that you're not looking at those. And here's my independent values. Here's my here's my independent values. Here's my dependent values. And I've got these in L1 and L2 in the calculator. And here is the graph of that with the line of best fit. We can see that. That's fine. Oh, I didn't have the correlation coefficient. Correlation coefficient is pretty strong here. And here is the residual plot. And we're looking at the residual plot because the whole goal here is to say, is a linear model appropriate in this situation? And as we look at the residual plot, we say, okay, is there a pattern to this? And the answer is no. So there's not. So a linear model is appropriate in this situation. But what we're going to do is we're going to take a look at what I've done with these data sets, because what I've done is for every other column here, I've applied some function to the values in L2. I've applied a function, like if you take a look at this C right here, the C column, it's the B column squared. 8 squared is 64, 3 squared is 9, 20 squared is 400, and so on. And so there's a function applied to it. And here is what we would see on the calculator. Now, we've got a correlation coefficient of 0.93 because as the graph works here, it looks very linear, but you really can't tell too much that there's a curve to this data set. But the correlation coefficient is 0.93, R squared is 0.87. Man, there's a really strong correlation. But if I take a look at the residual plot, the residual plot shows a definite pattern, so I know that a linear model is not appropriate. So what I would have to do in order to use a linear model here, I would have to in some way transform the data by applying some sort of function to it. So what I could do is, and you'll never have to do this, you'll never actually have to apply the functions yourself. Or if you do, they'll tell you what to do. But you'll never have to say, oh, what function do I apply here? But what you could do is you could take the data set, and for example, I would take the data set and take the square root, which would be the inverse function here. I would take the square root, and this residual plot would show me that, you know what, if I took the square root of that data set, I would end up without a linear pattern, and that would give me a situation where a linear model would be appropriate. So what you might end up seeing is a question that looks something like this. Here is your original graph of your data, and here's the residual plot, and it was determined that a linear model is not appropriate. So then it might give you like a couple different functions were applied to this data set, and is a linear model appropriate at this time? And then you would look at this and sit there and say, yes, a linear model is appropriate for the function applied to this data set, or the transformation that you've done, because the new residual plot does not have a pattern, so that therefore a linear model would be appropriate. Okay. Taking a look, this graph right here, or this data set, is the inverse of original L2. And we've got a correlation coefficient of negative 0.54, so it's, you know, it's a moderate correlation in a negative direction. And as we look at this, really you say, okay, I don't know if there's a pattern or not. But here, looking at the residual plot, you've got this curve going on here. So a linear model would not be appropriate. But if we did the transformation, and one of the transformations you can do is you could take an inverse. So if I took the inverse of this data set, I would get, again, it's my original plot, but it's the residual of this list right here, like L3. And this would say that it's appropriate. So what you can see is that when you have a data set that gives you a model, that when you look at the residual plot and it is not appropriate to use a linear model because you've got a pattern in the residuals, you can apply a function to that data set and try and linearize it, because we're talking about linear correlation. We're not talking about quadratic correlation. We're not talking about logarithmic correlation. We're talking about linear correlation. And what I can do is apply a function to the dependent variable and see if I can linearize it, meaning make a residual plot from after my function that says a linear model is appropriate. So that's what we're talking about. You will not have to do that. Now, typical functions that you would use would be like squaring or square root, logarithm, inverse. Those are really kind of like the four that you're going to talk about. E is not used that much. The natural logarithm isn't used that much. But squaring and square root, logarithm, and inverse. Those are the ones that would be used the most. And they would say, here's your original data set, here's your residual plot. Is a linear model appropriate? You'd say, no, it's not, because there's a pattern in the residuals. And then we'd say something later on, further on in the question, okay, so we applied this function of taking the inverse of the data set, and we got this. Is a linear model appropriate now? Yes, it is. Or they might give you a bunch of different graphs, say, which function would you use to come up with a linear model? And you'd have to look at, of the different function graphs, which one gave you the residual plot that said there's no pattern. That's really what chapter 10 is about. That's all we got.